Hello! Today we are going to take a look at experiment number 2. This experiment is about how solar panels perform in a parallel circuit versus a series circuit, how much power they produce and why. First, let's have a look at the components that we have included. As you can see, we again have a solar panel right here with us. And we have got a lamp again as well. A lamp stand. We can screw the lamp in now. Some cables. We have a multimeter that's still in its original packaging. We'll need to unpack it first, and then we'll be ready to begin with the experiment. So, we're going to proceed carefully, taking everything one step at a time. To start, we'll position the lamp right over here, and then we'll plug in the solar panel. As a first step, we need to determine the critical resistance. For that, we first need to connect the two panels in series. You might ask yourselves now, why two panels? Before, we always only had one. So, if we have solar panels on the roof, we have a large amount of those panels installed there, and that's why for experiment 2, we are going to simulate that. To find the critical value, we first plug the red cable from one panel into the red socket, and the black cable from the other panel into the other socket. Now, we just need to plug the two cables together, and then we'll have a series circuit. The critical value in this case is reached when both lamps, the green ones on the PV panel here, are just barely lit up. First, we switch on our lamp, so now we have to use the rotary resistor to find out where the critical value is. We can see this one lamp here turned off. That means precisely here is the critical resistance point, where both lamps are just barely lit up, and that's exactly what we need for the next step. Okay, for the next step, we're going to determine the terminal voltage for each of the two panels individually. To do this, we'll need the multimeter and two additional lab cables. First, we're going to take the red lab cable and either thread it through the existing cable or simply insert it, and then we'll connect the other end right on top, next to the variable resistor. We are going to take this end and plug it into the multimeter right here, so we can accurately measure the electrical voltage. As a next step, we are now using the black lab cable. We will connect it with the black lab cable that also comes from this panel, and we plug it in here. This is the connection between the two panels, and we insert it here. Now we will plug it in here into COM. This means that the cable runs along this specific path, then goes through here and directly into the panel. From the panel, the red cable goes out, passing through this section and connecting into the multimeter. So, right now we are going to set the multimeter to 20 volts, and then we will be able to read the values right here and note them into our table. And we're going to do the same thing now with the other PV panel. And after we have noted down both of these values, we will then measure the total terminal voltage of the two modules. To measure the total terminal voltage, we must connect our multimeter in between the panels. And specifically, we will connect the red cable to volt. And connect that, or rather, connect the two cables together before the resistor. We do the same with the black cable. We plug that into COM and connect it under the resistor, under the other cable. Hence, we connect the two cables together, and now we can turn this up to 20 volts. And at this point, we are seeing the total terminal voltage, and we will also note that value down in our table. If we take a closer look at these three values, we'll see that if you add up each of the individual terminal voltages, they will always result in the total terminal voltage. Did you know that? Pretty amazing, right? Now, our goal is to measure the electrical current in the series circuit. For this, we'll begin by measuring the electrical current between the rotary resistor, which is located right here, and a PV panel. What this means is that we will first unplug the cable that is currently connected just before the rotary resistor, and then we will proceed to plug it into this specific side, and after that we will also need one more cable. We plug this in here in front of the rotary resistor and connect it to COM. Now we've essentially inserted the multimeter in between before the two parts are connected, and we'll note down this value so we can compare it later. Alright, for the next step, we're going to measure the electrical current flowing between these two modules. That means specifically right in the middle between them. So first we'll unplug what we've just connected and assembled, and then we'll plug this red cable back into here. And now this part is quite straightforward. We're going to take these two pieces right here and pull them apart, and then we'll plug the black one into the COM socket and the red one right next to it, and we'll make sure to note down the value we get now. And when we look at them, we notice that both are almost identical, or even exactly identical. This means that the electrical current in the series circuit does not add up, but rather stays the same, regardless of whether we measure between the variable resistor and the PV module, or between the two PV modules themselves. This is important because now we'll take a look at the next experiment. Alright, so we've just finished measuring the individual voltage and current within our series circuit. Now we will measure the total system voltage and current. This is quite important because if solar panels are installed on a roof, multiple modules are connected together in a long string. We want to observe how the performance changes when, for example, a single module fails completely or if it becomes covered by shade or dirt. So, how does this impact specifically the voltage and the overall current? We're going to work with an arbitrary current level. We actually have a couple of options here. We could use this one right here, or we could go with this one over here. To show you the physical effect this has on the circuit, we are now going to simply pull these two components apart from each other, and we're going to plug these right into our multimeter, just as I demonstrated for you earlier. And then, additionally, we'll be measuring the overall total voltage on the second multimeter we have here. For this particular task, we're going to need another laboratory cable that is plugged in before the variable resistor, and then it goes into the multimeter. And another cable that gets plugged in after the rotary resistor and is also connected to the multimeter's socket. So, on this multimeter, the total voltage will now be measured. That means we turn the dial to volts. We can already see that it's showing 0 here. That can't be right. We must have made some kind of mistake. Okay, we'll try to turn on the other device. We'll set this one to amperes. Alright, so we've discovered that both measuring devices need to be switched on for the current to flow through, so that we actually have a complete circuit. Otherwise, no current will flow at all, and we won't be able to measure it. So we can now see both values here, and we can just note down both of them again. So, for our next step, we're going to grab something for covering the panel. You could use a piece of paper, but I would actually recommend that you take something where very little, or ideally no light, can pass through at all. And we can now hold this in front of one of the modules, specifically in such a way that one of them is completely covered. And then we'll observe how this affects the voltage and the amperage. So we'll place it like this in front of it, and you need to make sure that the entire module is completely covered. And we can now read the values from here, and we'll notice that it's in the 0 range. It doesn't go completely down to 0 because solar modules also produce a little bit of electricity from the back. That means it would also have to be completely covered from the back. But you can already see that we don't really have any current or voltage here. This means that it should be something in the 0 range. And now we can take a look at what happens when we cover both of them halfway. Let's hold this here in front of it as well. And we see that the current and the voltage are both very low. We can note down the values. So now why is that actually the case? Well, that's because, you see, it's an electrical circuit, and the readings that we observed here are always the readings that originate from the module, which produces the least amount of electricity. This means that if even a single panel on the roof gets damaged or ends up covered in shade, it's going to have a direct impact on every other module in that string in a series circuit. That creates a bottleneck for the entire system's efficiency. To see if there's a more resilient way to set this up, we're going to have a look at the parallel circuit and evaluate whether that configuration might actually be the better solution.